This is why we use electrolytic cells. We use them for rechargeable batteries, and we use them in the process of metal refining. So if we're looking at mining iron, or we're looking at mining gold, or we're looking at excuse me, mining nickel, or looking at mining called Luddite or something that they use for cell phones. Okay? It's a process where the anode is the impure metal and the cathode is the pure metal. So you'll have copper on one side and the ore, all the other junky stuff, on the other side. And so what happens is when we apply electricity, the anode breaks down and the pure copper is plated. So copper is going to move over the positive ions go to the cation or go to the cathode, the negative ions go to the anode. So the copper ions that are floating around in the water as that anode breaks down are going to go over to the electrode, the cathode, and plate it. They're going to stick to it. So you have two anodes or two electrodes in the solution. Potentially, let's say they're both carbon. One's going to break down. Well, one will be a copper. It'll break down into all the different pieces that are in that rock. So copper, maybe there's some zinc, maybe there's some manganese, whatever is natural in the Earth's crust. And then this one here, the cathode, will only attract the copper ions because we set that voltage, we set that cell potential, right? So this is what we look at here. Here we go. So if we had copper, okay, this is our impure metal here. And then what happens is it will break down. We'll have copper 2+ ions floating around in the water, and it will go and plate the other electrode as a pure metal. So this reaction here, when we go from a 0 to a 2+, is what half reaction? An oxidation number of 0 to an oxidation number of 2+. This is an oxidation reaction. And oxidation occurs at which electrode? Anode. So if I'm going from a 2+ oxidation number to a 0 oxidation number, what half reaction is this? Reduction. And it occurs at what electrode? Cathode. Okay? And what happens is you can go from a chunk of rock that's got 10 or 15 different metals in it to an electrode that's 99.999% pure. Now, the downside to this is the solution. So the downside to this process, though, when we look at an electrolytic cell, here's the cathode and the anode. So this is the impure copper. Here's the cathode where it's going to collect the pure copper. Here's the battery in between. And what happens is in the tank, all of the unused stuff goes to the bottom in the form of a sludge. And the water has the floating ions in it. And so it becomes a waste disposal nightmare. In that, they create these huge, what they call tailings ponds. So tailings is where all of the waste stuff goes. You've probably heard about it in gold mining, where they have, and they talk about how the birds landed in the tailings pond and they all died, or they talk about it in the copper mines in BC, central BC. They have these wastes in them, and these wastes have what we call heavy metals. So zinc, copper, manganese, iron, those are all what we consider heavy metals. Because sodium, potassium, lithium, those are also metals. But we don't call those heavy metals because they're readily available right near the surface of the earth. Whereas iron and zinc and manganese, those you have to dig down and get them. Gold, you have to dig down and get them. And so we call those heavy metals. And they have this waste that's toxic, that contains all of these other metals that you have no use for. There's no way to recover them and find a secondary or a tertiary use for them. And you just get this big collection of pits. Now, science has moved those industries along, the gold mining industry and the iron industry, the copper industry. It's moved them along, and they've now got technologies where they can clean up the water, but the sludge sticks around, and you can't spread it on the land because the land can only tolerate a certain percentage of those metals. Plants can only tolerate that. Animals can only tolerate that. So this is the downside to electrolysis, is all of this extra waste. Okay? Another common use of electrolysis is electroplating. So I don't know, well, Sydney might, because she's really into cars. But how many people here have chrome-plated stuff on their vehicles? Okay? The really shiny, shiny metal on vehicles is called chrome plating. And so what they do is they take a metal and they dip it in, and it's electrolyzed, and it's got this current going through it. And what you put into there acts as the cathode, and the solution is the anode, and it plates it. Okay? How many people wear gold-plated earrings? If you could scratch that gold leaf off, inside would just be a common metal. How about silver-plated? Or there's a multiple things that we plate. Okay? So the other thing that we do with electroplating is, remember when we talked about corrosion, we had the sacrificial anode so that it would go after that metal first before it went after our actual vehicle or went after our hot water tank. This is the same idea. It will create a layer around the object so that the object doesn't break down. Stainless steel. If you put water into a regular metal bin, what's going to happen? It will rust. But then we do this electroplating piece and we create this stainless steel, and it puts a coating on the bin. And we can store water in that bin for however long, or in the culvert or whatever. Okay, it's how we can use our forks with our food and they don't break down. If you flip your fork over on your set, chances are you will see stamped into it stainless steel. Okay, they're coated so that they don't break down. We electroplate utensils with silver. We electroplate jewelry with gold. Lots of different pieces about it. For electroplating, the object that's being plated or coated has to be the cathode. Okay? So that means that the anode is the metal you want to coat it with, so the plating metal. So let's look at plating a spoon. This is our beaker, slightly over exaggerated. Here's an electrode. And here's our spoon. Okay? Let's look at this piece here. This is a symbol for a battery. From Physics 30, which side is positive and which side is negative? The long line is positive and the short line is negative. Which way are the electrons going to flow? They're going to flow this way. Okay, so if this is the flow of electrodes, what is this spoon then? Okay, right? It flows out of the anode and into the cathode. Positive or negative goes into the positive. Okay, so the spoon is our cathode. It says that we want the object to be plated to be the cathode. If it's the cathode, which half reaction is this? It's electrolytic. Okay, which means that at the anode we have oxidation. So we have the oxidation half reaction at the anode. Now the anode is going to break down and give us our silver ions. Our cathode is what gets plated. So we're going to take our silver ions that are floating around, 1 plus, and plate it with silver, pure silver. Okay? Yeah. So our solution is probably something like this, silver nitrate. And why? Because nitrate is aqueous with all things that bond to it. Pardon me? Yeah. You could, yeah, if you wanted this spoon to be plated in gold, you would stick a gold anode in there. So this is going to be silver. And this is going to be our spoon to be plated. Hang on. Yeah, the object that is being plated is the cathode, and the anode is the metal that you want to coat it with. So we want to coat it with silver, so we're going to stick a silver stick of metal in there. We're going to turn on the electricity, and the spoon is going to come out silver. So what do we notice about the oxidation and the reduction reactions? They're the inverse of each other. Yeah. We can have that happen because in this particular case, our strong oxidizing agent is less than our strong reducing agent.